Hello everyone. In this video we look at the idea of a system of particles and some of the internal phenomena which broadly classify into the two categories. One is collisions and second is explosion. We will deal with system of particles in much more detail when we go to the center of mass idea, but here we'll try to understand the system of particles behavior more to know about the internal phenomena, because collisions is one of the important phenomena in physics that we'll be discussing. Now when we look at system of particles, what we are essentially saying is in both kinematics as well as in the laws of motion and work energy, we've been mainly talking about the point mass. So point mass is supposed to occupy a single location, and the volume occupied by the object is supposed to be negligible. That is what we are looking at as a point mass. But you may have not just one particle but a group of particles. Here we are looking at a particle of mass m1, mass m2, mass m3, mass m4 and so on. Here we are looking at the case where we have countable number of particles. If you look at normally what is an distributed mass system, like the common objects we look at, so this is what we call as a distributed mass system. The common objects that we'll be looking at, these distributed mass systems are supposed to have infinite number of particles. We'll talk more about this when we go to the center of mass idea, but here we are trying to understand the behavior of system of particles more from a point of view where we are having countable number of particles. So let us say we have countable number of particles. Maybe the total number of particles is 2 or 3 or 4 or 5, 10, even 1 lakh, but it must be countable. So if you look at the total momentum of this system of particles, since momentum is a vector, we must add the momentum values of each and every particle. So m1 v1 bar plus m2 v2 bar, m3 v3 bar and so on. So if we are finally having n number of particles, it will be mn vn bar. This will be the total momentum of the system of particles. Of course, we have to keep one thing in mind, that we need to be adding the momentum like vector, because momentum is a vector quantity. So we cannot just add these quantities like numbers. We have to follow the vector law of addition. So in fact, we can represent this m1 v1 bar as p1 bar, m2 v2 bar as p2 bar and so on up to pn bar. So this is what will be the total momentum of system of particles. Now when we look at the rate of change of momentum, so let us say we assume that the total momentum of the system is changing, then the change in momentum of the total system by the time taken will be the rate of change of momentum. It will be equal to the rate of change of momentum in the first particle plus rate of change of momentum for the second particle and so on, rate of change of momentum for the nth particle. So rate of change of momentum of any particle will be the force acting on the particular particle. So rate of change of momentum for the second particle will be force acting on the second particle and so on. We have force acting on the nth particle. So total system momentum rate of change will be equal to force acting on the first particle plus force acting on the second particle and so on up to force acting on the nth particle. Now when we look at force acting on the first particle, let us say this is the first particle, we have second particle, third particle and so on. The force acting on the first particle may come from two sources. It may come from the external source or it may come from any of the internal sources. When we say internal sources, we mean to say the other particles of the system that we are considering. So which means force acting on the first particle will have two parts. Force acting on the first particle because of external sources, because of the internal sources. Similarly, force acting on second particle we'll also have the external part, we'll have internal part, and so on. Similarly, the nth particle also, force acting on the nth particle will have the external part as well as the internal part. Now when we look at the nature of the internal forces, let us say particle 2 is exerting a force on particle 1. Then as per the Newton's third law, particle 1 will in turn exert a force on particle 2, which will be equal in terms of magnitude but opposite in terms of direction. So this is what we call as the action reaction pair. Now if we are measuring action in the force acting on the first particle because of the internal sources, then the reaction for this will be measured in force acting on particle 2 because of the internal sources. Thereby, if we add up all these internal source, then we are essentially adding up all these action reaction pairs, which means we will be adding up a force with another force which is exactly equal in terms of magnitude but opposite in terms of direction. So the total value of all these internal components of the force will add up to 0, because essentially we are adding the action reaction pairs. Now what we will be left with is force acting on first particle because of the external source, force acting on the second particle because of the external source, and so on, force acting on the nth particle because of the external source. So this we can write it as the total external force, the sum of the external forces acting on each and every particle. When we add it up, we can say this is the total external force acting on the system of particles. This will be equal to the rate of change of momentum for the entire system. Now the significance of this formula is, if we look at internal phenomena. So when we talk about what is an internal phenomena, a process where only the particles we are considering to be a system are engaging themselves without any external force being present. So here we'll talk about two such examples. One is what we have as collision, where particles moving would change their direction of motion and also their velocities after an interaction which we call as collision. And second one, an object will explode into small parts which we call as the explosion. So both these phenomena, there will be no external force present. If there is no external force present, then what we would conclude is the total external force value will be 0. Thereby the rate of change of momentum for the entire system should be 0, which would translate into the change in momentum for the entire system should be 0, which would mean that for the entire system, whatever is the initial total momentum should be equal to the final total momentum of the entire system. Now the individual particles of the system, so a system might have 5 particles or 10 particles, individual particles might have a change in the momentum values because of the interactions involved in between the particles, but the system as a whole, the initial momentum or final momentum would be same, which means essentially when we add up all the momentum values of particles, the total value is going to remain same. And that is what we look at in case of internal phenomena like the collisions and explosion. So we'll just give a brief idea in terms of what is a collision and what is an explosion, as anyway in the next video we'll be looking into the details of both these phenomena. Collisions basically are defined as a phenomena where two or more particles would interact with each other, which we call as the process of collision, after which we see that the particles would change their velocities, maybe in terms of direction, maybe in terms of the value, or both. And this process essentially is an internal process with no external force being present, which means if you look at the total momentum of the particles involved before the collision. Before the collision is taking place, if you look at the total momentum of the particles, that must be equal to the total momentum of particles after the collision. So this is what we look at in terms of collision. So we'll go into the details of collision in the next video, but this is to understand what essentially will be happening in a collision process. Now when it comes to explosion, here as we said, we have a large object which might break down into two or more pieces. Now initially the object may be at rest or it may be moving, which means the object will be having some momentum. So here also the total initial momentum, if it is at rest, means the initial momentum will be 0. After the explosion happened, we'll have the constituent particles which will be coming out. The total momentum of particles after the explosion and the initial momentum before the explosion, these two also must be same, because explosion is also an internal phenomena. So this is about the way we will deal with system of particles and the internal phenomena relating the system of particles.